need different types of energy sources in order to survive. In modern life, electrical energy is an indispensable source of energy. Electricity is generated by power stations and transmitted through cables to households to drive various electrical appliances to serve people. The electrical appliances that we use in our daily life, such as the rice cooker, iron, toaster and fan, have to be connected to a power supply. How do electrical appliances operate on electrical power? Most domestic electrical appliances are designed in such a way that an electric current passing through the parts can generate heating effect or magnetic effect. Connect a resistance coil with an ammeter and a rheostat. Then connect to a power supply. The point of the ammeter moves on the dial, showing that there is an electric current passing through the resistance coil. The resistance coil heats up and glows. Adjust the rheostat to increase the current passing through the resistance coil. The resistance coil releases more heat and light. When an electric current passes through a resistance coil, the electric energy converts into heat energy. This is known as the heating effect of current. Connect a power supply with a copper wire. Then connect another power supply to a nichrome wire of the same size but higher resistance. After connecting the two circuits, adjust the voltage so that the current flowing through the copper wire is the same as that flowing through the nichrome wire. A moment later, the copper wire does not release light and heat. But it is obvious that the nichrome wire releases light and heat. From the above experiment, we can infer that if the same electric current flows through two pieces of metal wire, the heating effect is stronger for the wire with a higher resistance. The metal wire with a high resistance is known as a resistance coil or a heating coil because it can heat up. The heating effect of an electric current is the basis on which many electrical appliances generate heat and light. An electric heater makes use of a heating coil to generate heat. Switch on the heater. The heating coil soon glows and turns red hot. A hairdryer makes use of a small fan to blow hot air. Dismantle the dryer and you can see the heating element on the front and the fan at the back. After the dryer is switched on, an electric current flows through the heating element. As a result of the heating effect of the current, the heating element heats up. Switch the dryer to high power. The electric current passing through the heating element becomes stronger and more heat energy is released from the heating element. With the stronger wind from the fan, the dryer can blow hotter air at a higher speed. Similarly, an electric radiator uses a heating wire and a fan to blow warm air. Put a piece of bread into a toaster. In a minute, a nice piece of toast springs out. A toaster also makes use of a heating element to generate heat for toasting. The heating element of a toaster is twisted around a thin piece of insulation. Put a slice of bread into the toaster, push the button, and the current is connected. When the electric current passes through the heating element, heat is generated from the heating element to toast the bread. An electric kettle is another domestic electrical appliance that uses a heating wire to generate heat. When the kettle is switched on, the heating wire begins to heat up. Bubbles form around the heating wire. The temperature of the water begins to rise. Water is a conductor, and the heating wire is in direct contact with the water. Why is it that there is no electrical leakage? The heating element in the kettle is made up of a metallic tube. If we cut open the tube, we can see that the tube encloses the heating wire, and that there is a layer of white insulation between the tube and the wire. The purpose of the insulation is to separate the heating wire from the metallic tube to prevent electrical leakage. When an electric current passes through the heating wire generates heat, which is conducted to the metallic tube. The hot metallic tube then heats up and boils water in the kettle. An iron and a rice cooker also use a heating coil to generate heat. The heating elements in these two appliances are hidden inside and are separated from the other metallic parts by insulation. When switched on, the heating elements generate heat and heat up the metallic parts of the cooker or the iron for cooking rice or ironing clothes. When an electrical appliance is switched on, an electric current passes through the various components in a circuit, and a piece of magnet generates a magnetic force around it. Connect both ends of a long conducting wire to a power supply. The ammeter shows that there is an electric current passing through. Place a compass under the conducting wire. The compass needle moves. Switch off the power supply and the compass needle returns to its original position. Connect the power supply again and the compass needle moves once more. If we increase the current that passes through the conducting wire, the needle moves more. So, there is a relation between the electric current and magnetic force. An electric current passing through a conducting wire can generate a magnetic force. The stronger the electric current, the stronger the magnetic force created. The generation of magnetic force by a conducting wire carrying a current is known as the magnetic effect of current. Place this bar magnet near a pile of iron nails. The bar magnet attracts the iron nails with its magnetic force. Sprinkle iron filings around a solenoid made up of copper wire. When the solenoid is connected to a power supply, the iron filings form lines within and around the solenoid. This shows that a magnetic field is set up around the solenoid as a result of the magnetic effect of current. When a solenoid is connected to a power supply, it can also attract iron nails. By increasing the current passing through the solenoid, we can see that the solenoid attracts more iron nails. This shows that the stronger the current, the stronger the magnetic field set up by the solenoid. When an electric current passes through a solenoid, a magnetic effect, similar to that of a magnet, is generated. A device that generates a magnetic effect after being connected to a power supply is known as an electromagnet. A doorbell is an example of the application of the magnetic effect of current. The major component of an electric doorbell is an electromagnet. There is a steel strip connected to a small hammer. When an electric current passes through the doorbell, The electromagnet generates magnetic force and attracts the hammer so that it hits the bell to make a sound. As the steel strip is attracted by the electromagnet, the circuit is open and the electric current is cut. As the current is cut, the electromagnet no longer generates magnetic force. The steel strip bounces back to its original position. The circuit is then closed again, and the electric current flows through the circuit. So, the electric current flows intermittently, and the hammer hits the bell incessantly to make a sound. A moving coil loudspeaker makes use of the magnetic field of a magnet acting on a solenoid connected to a power supply. It can be gathered from its name that a moving coil loudspeaker has a coil that vibrates freely. The coil is housed in a cylindrical magnet. When an alternating current passes through the coil is pushed in and out by the action of the magnetic field on the coil, making the cone connected to the coil vibrate and give out sound waves. Place an aluminium rod on two parallel copper rails. Place two magnets with different poles facing each other above and below the rails. A magnetic field with field lines perpendicular to the rod is formed. Connect the two ends of the copper rails to a power supply. The rod then rolls forth as if pushed by an invisible force. The movement of the rod on the copper rails is in fact a result of the interaction between the current-carrying conducting wire and the magnetic field of the magnet. When the apparatus is connected to a power supply, an electric current flows along the copper rails and through the rod. At this moment, the magnetic field set up by the magnet acts on the electric current in the rod. Magnetic force is generated and pushes the rod forward. If we reverse the polarity of the magnet, or reverse the current, the rod will roll in the opposite direction. The interaction between a magnet and a current-carrying conducting wire can result in a continuous rotating motion. A current-carrying conducting wire will experience magnetic force in a magnetic field. Wind the wire around a rectangular former to form a rectangular coil and connect both ends of the wire to a power supply. Place the coil between the two poles of the magnet. When the conducting wire is connected to a power supply, a magnetic force is created as a result of the magnetic effect acting on the conducting wire. The magnetic force acting on the coil makes the coil rotate. This apparatus, which rotates because of the magnetic effect by a magnetic field on a current, is known as a motor. A motor is a device to convert electrical energy into kinetic energy. In daily life, the motor is used in many electrical appliances. In an electric fan, for example, there is a motor. The motor in an electric fan is more complicated in its structure. However, it follows the basic design of an iron core in the center with insulated conducting wires wound around. The whole set is housed inside a magnet. Connected to a power supply, the coil, together with the core, rotates under the magnetic effect of the magnetic field on the current-carrying conducting wire. By increasing the current passing through the fan, we can make the fan turn faster. All motor-driven domestic electrical appliances consist of a rotating part. For example, an exhaust fan, a washing machine, a blender and a disc player. The refrigerator, the air conditioner and the vacuum cleaner are also driven by motors. Some domestic electrical appliances may have a number inscribed on the surface. For example, the number 1200 is marked on a hairdryer. This number is not the price, but the power of the appliance. The performance of an appliance is closely related to its power. Power is the quantity of electric energy supplied to the appliance in 1 second. The unit of power is a watt, and the symbol is W. The number 1200 means that the power of the dryer is 1200 watts. The power of an electric fan is 200 watts. The power of an ordinary light bulb is around 40 to 100 watts. The power of a television set is 100 watts. The power of heating devices, such as kettles, irons and ovens, range from 1000 to 2000 watts. Different electrical appliances use different quantities of power. Given the same voltage, the larger the power usage of an electrical appliance, the stronger is the current passing through it. For example, the current passing through an electric kettle is stronger than that passing through an electric fan. This is because the power of a kettle is a dozen times that of a fan. We can use this formula to calculate the electric current passing through an electrical appliance. Current equals power over voltage. For example, plug a fan of 150 watts to a socket of 220 volts. The current passing through the fan is equal to 150 watts divided by 220 volts, or approximately 0.7 ampere. Plug an electric kettle of 1000 watts to the socket. The current passing through the kettle is equal to 1000 watts divided by 220 volts, or approximately 4.5 amperes. If we know the power rating of an electrical appliance, we can calculate the amount of electrical energy consumed according to the length of time during which the appliance is used. When electricity is supplied to a household flat, the electric power company installs a kilowatt-hour meter in the household. A kilowatt-hour meter is used to measure the electrical energy consumed by electrical appliances. We can calculate the amount on our electricity bill by multiplying the charge per unit and the number of units of energy consumed as recorded by the kilowatt-hour meter.